Hi, folks. It is Tuesday, July 14th. I'm going to start by going over some of the questions from the quiz that was due over the weekend. Give me a sec to switch over to that, and then take a look at related rates and optimization as folks would like to. Let's pull up that quiz here. Okay, so I think I'm just going to talk through the first 5 questions here. I tried to give some feedback to folks who got these wrong, and I will say, these are interpretation questions. You can make an argument maybe on 1 or 2 of these that there's more than one possible meaning here. But let's just run through these one at a time. So statement A, the concentration of a drug in a patient's bloodstream changed from 0.17 milligram per cubic centimeter to 0.09 milligrams per cubic centimeter over the course of 2 hours. So the key word here is that this happened over the course of 2 hours. Anytime there's a finite measurable amount of time involved, it's going to be an average rate of change if what we're talking about is the concentration of a drug in this case. There's the last question, we'll talk about that a little bit more, but yeah. What's happened here is a healthcare worker has taken a measurement at one point in time and then another point in time 2 hours later and calculated the change in concentration over the change in time. So average rate of change. B, since 1975, when this icon of the American West was listed as an endangered species, grizzlies in Yellowstone National Park ecosystem to the south have more than quadrupled their population. Okay, so just like the first one here, period of time that's elapsed. So we're going to call that an average rate of change. This rate of change has been over several decades here. Statement C, Montana currently has the highest growth rate in COVID-19 cases of any state. First of all, don't panic. That was a day-over-day percentage increase from last week. It was a correct statistic, but really the reason that we have that statistic is originally we had a very low rate of infection, and that has come up a little bit, percentage-wise increase. It was the greatest of any state, including DC and Puerto Rico for one day. And that's about as close to an instantaneous rate of change that we could get for measuring COVID-19 cases. Again, technically, if someone wanted to debate this with me, I would hear them out on it because, statistics are only calculated on a daily basis. Is it really an instantaneous rate of change? I'd say it's about as close as we can get here for this particular measurement. All right, part D, the Dow Jones Industrial Index has lost 3,000 points since January 1st, 2020. Again, there's a finite amount of time that's elapsed for that rate of change, so it's an average rate of change. And then question E might have been the trickiest one. This is a stat I looked up. So in 2019, the exit velocity of Chris Sale's fastball was on average 81.1 miles per hour. Okay, and I think what makes this one tricky is the word average is in the statement there. And so immediately everyone's thinking, okay, is this maybe an average rate of change? And I could have rewritten this statement in a way that it would be about an average rate of change. If, for example, Chris Sale's fastball got slower over the course of that season, like on opening day, it was something, and then by the end of the season, it had decreased or it increased or whatever, that would be an average rate of change in his fastball speed over the course of a season. But what this stat is really talking about is how fast the ball is going the moment it leaves his hand, right? So that's the exit velocity for a fastball. So because it's a moment in time, moment is just an English word that we use to sort of mean an instantaneous measurement or an infinitesimal amount of time that's elapsed, when we've made that measurement. So best answer there is instantaneous rate of change. I kept these pretty low stakes, but I do think these questions are really important because they push you to not just learn how to solve some problems, but interpret where calculus might be operating in the world around you, within your field of study, within your major. So good. I'd be happy to talk about these with you more if you'd like. I'm going to jump into the other questions here. Let's see if I can go to my whiteboard. Okay, we are starting now. All right, so we'll have to jump back and forth here. So the next 3 problems, 2A, 2B, and 2C, all have to do with derivative rules. And there's more than one way to do some of these problems here. I left feedback on many quizzes where people got the correct answer, but I wanted them to know that there's an easier way to do the problem. So I'm going to start with 2A here, and yell at me if I'm writing off of the visible screen here. But 2A asks you to find d dx of the following expression, x squared minus 3 times the square root of x. Okay, and just some basic comments. I think we're all on the same page here. But first, the notation d dx. We don't really even think of that as a fraction. That's not like dividing by x. The d's don't cancel. They're not variables. It's an operator. It's telling us that we're supposed to take the derivative with respect to x of the following expression there. Okay, so what do we have here? We have x squared. Well, that's a pretty easy derivative. And then I have minus 3 times the square root of x. So what I'm going to do, and what you should do every time you see roots involved, is to rewrite them as powers of x. So I'm going to rewrite this problem, keep x squared, and then rewrite this as 3 times x to the 1/2 power. Right, and I know that was one of the things in the prerequisite problems talking about fractional exponents. Just a good reminder there. The 1/2 power is the square root. The 1/3 power is a cube root. The 1/17 power is a 1/17 or a 17th root. The problems we see are really limited to square roots and cube roots from what I've seen here. So the reason I do that is it's very easy to take derivatives of powers of x. And I know that if you go online and you ask a solver to do this, you ask it to do, okay, what's the derivative of the square root of x? It will tell you this. It'll tell you that that's 1/2 times the square root of x. And this is correct. However, this skips the understanding part, right? This gives you the answer without the understanding of like how to get that answer on your own. And I saw on some quizzes that people probably, because you guys are learning this on your own, and some people even cited some outside sources, I saw this step going from here to here quite a bit. And I just want to make sure that we have this understanding piece of how to do this in general. And that's just to rewrite it as a power of x. Throughout all of calculus, we really don't like roots. We like to have powers, right? Because all the different tricks that we're going to use for derivatives and later on for integration are going to be really nice and easy when we have powers of x. So that's how I'm going to do this problem. Give me one sec here just to switch apps. Sure, it's still visible. Okay, so, all right, so derivative of x squared, that's pretty easy. That's just 2x, right? And now using the same rule, we're going to take that power of x, pop it out in front, and then decrease the power by 1. So minus, and you don't have to write this like this 1/2 times 3. You can write it as 3/2 all in one step. That's fine with me. So the 1/2 is coming out in front. It's still being subtracted. And then we're going to decrease that power by 1. So 1/2 minus 1 is negative 1/2. And by the way, if you write it like this, full credit. There are many people I think who thought maybe they needed to go beyond this, but this is fine. It's a little bit weird if you have something like 1 + 1 still written in the problem there, but you don't need to combine like terms. You don't need to do anything with it. We're just we want to give you feedback and grade you on the calculus, and don't add any extra steps there. So this could be my final answer, or a lot of people also had this 2x minus 3/2 x to the negative 1/2. You also don't need to rewrite that as a positive 1/2. You don't need to write like 1/x to the 1/2. It's just fine the way it is. So just leave it. Okay, so there's problem 2A, and then problem 2B. I'm going to erase this so we have enough room for 2B. So 2B is an interesting one. 2B is a problem that's written as a quotient. So here's what you were given. So I take d dx of this expression 5x cubed minus 2x squared all over x. Okay, and so 2 ways to do this. It's written as a quotient. You can jump right in and use the quotient rule. Full credit, totally fine. But the quotient rule is kind of a pain in the butt, and especially if we had a complicated function in the denominator here, we might want to avoid doing that if possible. So we can always do valid algebra steps before we differentiate. Like I can mess around with this fraction as long as I'm using valid rules of mathematics before I take my derivative. And what you'll see here is the numerator has 5x cubed minus 2x squared. So those both have a common factor of x. So I can complete this division, right? The division that's inherent in this fraction here before I take the derivative. So if I take 5x cubed minus 2x squared and I divide each of those terms by x, right, which is what we have written here, well, then I have a new expression that's going to be easier to differentiate. So if I take 5x cubed and divide by x, I'm left with 5x squared. If I take negative 2x squared and divide by x, I have negative 2x. And a lot of people saw this. A lot of people saw this shortcut and took it. Other people use the quotient rule. You're going to get answers that look a little bit different, but that are mathematically equivalent. So if I do it this way, take the derivative of 5x squared, the 2 comes out in front, so I have 10x, right? 2 times 5 is 10. And then my minus 2x, when I differentiate, that power of x goes from 1 down to 0, and so I just have minus 2. So that's definitely the fastest way to do it. If you did do the quotient rule, so I'll just switch colors here. So if you went directly to the quotient rule, well, quotient rule is low d high, so x times d dx of the top. And when I do these problems, I actually do like to write all of this out. I don't try and take all my derivatives at once. I'm going to write the quotient rule without taking derivatives, and then take the derivatives that I need to. So this is that low d high minus high. So high is 5x cubed minus 2x squared. D low, so times d dx of x. And that's an easy one, but I'm still going to write it out. And then the whole thing is over low squared, so over x squared. All right, so now, although it's kind of messy, there's a lot going on here, I can see exactly what I need to do to finish the problem. I need to take this derivative, I need to take that derivative. And once I've done that, my problem is done. Okay, so x times, it's really important that this entire function is in parentheses, right? In both spots here, we don't want just part of the function getting multiplied by part of the derivative. So x times the derivative of 5x cubed, so 15x squared, minus 4x, and then we're going to subtract 5x cubed minus 2x squared times the derivative of x, which is just 1. Right, so that's not going to change that at all. And then the whole thing is divided by x squared. And I'm not going to take up your time or more video time showing that these two things are equivalent. But if we distributed, if we collected like terms, if we divided by that x squared, we're going to end up getting the exact same thing, that 10x minus 2. It's fine if you end up using the quotient rule in a problem like this. It's fine to leave it just like this. You don't have to do anything else beyond that. So there's 2b. 2c involves a product. So I'll write that one up here. And again, I saw a number of people who decided to multiply this out, which is a lot of work. It's a type of work that like a computer doesn't mind doing. So sometimes if you use Symbol Lab or something like that, it will just say, oh, no problem. I don't mind multiplying trinomials by trinomials. But when we humans are doing this problem, it's definitely easier to use derivative rules than to expand this whole thing out. So, and I tried to write a problem here. Same thing with the quotient problem. I tried to write problems where it was possible to do it more than one way, but it was kind of a pain, right? There's definitely like an incentive to use the helpful derivative rules here. So we're going to take d dx of this following product here, right? So two things multiplied together. I think that's really the first thing to recognize is that what we have here is two functions, right? Here's a function, we could call it f, call it whatever we want. We could call that one g. It's two things multiplied together. And so we can use the product rule. And the product rule is going to be pretty quick and easy here. If I don't use the product rule, if I try and do this multiplication, I'm actually going to end up with that 3x squared times all three of these, that times all three of these, that times all, we're going to have like 9 different terms that we then need to wrangle and collect like terms, and it's going to be a little bit of a pain in the butt. Okay, so if I use the product rule, I'm going to take the first times the derivative of the second. So my derivative then would be f times g prime, and then add that to f prime times g, right? Okay, well, I've just written it out sort of in its formula form, and I have f and I have g. So really all I need to finish this problem is to find f prime and g prime and then just plug them into this formula here. So if f is 3x squared minus 2x plus 1, then f prime would be 6x minus 2, right? So 6x comes from that term, minus 2 comes from that term, and the derivative of 1 is just 0. So there's my f prime, and then g prime. I'm just going to go term by term. So derivative of x squared is 2x. Derivative of x cubed is 3x squared, and the derivative of 2 is 0. So here are the remaining 2 ingredients for the 4 things that I need to finish this product rule problem. So my final answer then is my function f, so 3x squared minus 2x plus 1 times the derivative of g, and again, making sure that that whole derivative ends up in parentheses here, so times 2x plus 3x squared, and then add that to f prime, so 6x minus 2 times g. I'm running out of room a little bit here, so x squared plus x cubed plus 2. And just like the last problem, leave it like this. We're done. And in fact, if you can imagine grading these, it's much easier for me to look and see like, oh, there's f, right? There's that first piece and there's the derivative of the second. If you start multiplying this out and combining like terms and it goes wrong, you end up with a different answer. I might not even be able to figure out where your multiplication error was. So this is good place to leave the problem. So those are the 3 problems I had on derivative rules. The one that I kind of wish I'd put into this quiz, I know you got a lot of practice in WebAssign with it, but I probably should have put in this quiz, is a chain rule problem or 2. On last Thursday, I did some chain rule problems in conjunction with implicit differentiation. So we took a look at some of those in the live session, but there weren't any problems like that on the quiz. I'm going to put one of those and maybe also a differential problem on this week's quiz, even though they're topics from last week. I'll try and do like one short one of each of those just so you can get some feedback on those types of problems. Okay, so 2 more problems here. One is an implicit differentiation problem. It's problem 3. And I have given you a mathematical relation. It says it's a function. It's not really a function, right? Y is not a function of x. X is not a function of y. It fails the vertical line test, but we have this mathematical relationship between x and y, that x squared minus 1 equals y squared minus xy. And I did provide a graph of it. You don't need the graph to do this problem, but it might be a little bit helpful when you finally come up with your equation for the line or for the slope of the line. You can look on the graph and see if that makes sense, see if that's like a reasonable estimate of the slope of a tangent line. So yeah, we want to do 2 things. In part A, we want to calculate dy dx, and then in part B, we're going to find the equation for the tangent line at a particular point. So to find dy dx, I'm going to take the derivative of both sides of this equation with respect to x. So I'm going to take d dx of x squared minus 1 and take d dx of y squared minus xy. All right, and because we already knew that x squared minus 1 is equal to y squared minus xy, their derivatives have to be equal as well. Okay, so left-hand side is easy. We don't really need any special rules or implicit differentiation. We can take the derivative of x squared, that's 2x, and minus 1 is just 0. So on the left-hand side of this equation, we have 2x by itself. Now on the right-hand side, it gets a little bit tricky. We're going to have to do a couple things. We're going to have to use chain rule on y squared. And just to illustrate this briefly, over on the side, I think it's hard when we just have the variable y to see why we need to use the chain rule. But if this was f of x that was then squared, right? Now we really see that composite function structure. We have like, there's one function and then something else happens to it, gets squared after the function f occurs. Well, f of x and y, we tend to use those variables interchangeably to represent some relationship, right, between x and y. So the fact that this is y squared, well, okay, yeah, it's y squared, it's something being squared, but what it is a function being squared. And so when we take its derivative, we have to use chain rule. So when we take the derivative of some function squared, we still use that same property. We're going to take the exponent out in front. So 2 is going to come out in front. and then the power of y is going to drop down from 2 to 1. So we have 2 times y to the first power, which is just y. And then the chain rule says that when we've done that to a function, we need to multiply by the derivative of that inside function. And we have a word for that, or we have a symbol for that. The derivative of y is just y prime, or if you prefer dy dx. The problem has asked you to find dy dx. It's okay if you use y prime to stand in for dy dx. They mean the same thing. So the derivative of y squared is 2y times y prime. Okay, still have one more term here. I have this minus xy. So y is a function of x and x is a variable. So this is a product, right? This is a product for which we're going to need to use the product rule to differentiate here. And it's also a little bit tricky because it's being subtracted. So we want to make sure that what results from that product rule, the entire thing gets subtracted. So product rule says take your first times the derivative of the second. So x times y prime, right? When we take d dx of y, we get y prime. And then we're going to add that to the second, so y times d dx of x. Well, d dx of x is 1, and y times 1 is just y. And so here's what we end up with. We end up with this equation that has x's, y's, and y primes in it. To finish the problem, we need to get y prime by itself, and that just takes a little bit of algebra here. So first thing I'm going to do, I'm going to cheat a little bit because I have a dry erase board. I know I need to subtract these two terms, so instead of writing it as a separate step, I'm going to subtract that xy prime, and I'm also going to subtract that y just to do that distribution, because I'm going to want to get my y primes on one side of the equation and my other variables on the other side. Okay, so now I have a y prime here, I have a y prime there. There's no y primes on the left-hand side, so what I want to do then is get all the other variables over to the left if possible. So I'm going to add y to both sides, so now I have 2x plus y equals 2y y prime minus x y prime. Whoops. And now this is the key step. And I think this is the step that in the past I just seen a lot of students who like get a little bit into it and then they just can't quite finish the solving for y prime. The reason we want all our terms with y prime on one side is so we can factor that y prime out of them. If we factor out a y prime, we have 2y minus x left over on the right here. And now we're one step away from having our derivative. So to get y prime by itself, we're going to divide both sides by 2y minus x. So then I have 2x plus y divided by 2y minus x. And again, we just stop. And definitely don't do any bad canceling, right? We can't like cross out x's and y's here. These things are being added and subtracted. We can only do cancellation in a fraction if we have multiplication of a common factor there. So here's our answer to part A. And remember a few things about the derivative. Remember that the derivative is a function that gives the instantaneous rate of change. It is the limit of a difference quotient, but it's also the slope of a tangent line to the curve. Now, I'm going to jump back to the quiz here, hopefully, if I can remember the right keystrokes. Okay, so here's the quiz again, and then here's this graph. And what you might notice here is there's 2 points on this graph when x equals 2. It appears that there's a point on the curve at 2, negative 1, and there's another one at 2, 3. And if you can visualize a tangent line at those 2 points, you're going to have totally different slopes, right? The one down here at 2, negative 1, that one is going to have a tangent line with negative slope, and the one at 2, 3 is going to have a tangent line with positive slope heading upwards. So it should make sense then that our derivative here has both x and y involved in it, right? Because if it just had x, well, those 2 points would have the same derivative because they have the same x value. So we're going to see this quite a bit, that both x and y come into play if we started with some mathematical relation that's not a function. So part B asks us to find the equation of the tangent line, and I think we can do that just in the remaining space over here. I will switch colors so we don't confuse it. So I need 2 things to find the equation of a line. I need to know the line's slope, and I need to know a point on that line. I don't need the y-intercept. The y-intercept is one of many points that we could use. since we know that the point 2 comma 3 is on the curve that's been given to us in part B, we're going to use that point. And what we're going to use is point slope form. It's really handy in calculus because we do a lot of stuff with tangent lines. And so point slope form, just as a reminder here, is y minus y1 equals m times x minus x1. And then we use the ordered pair x1 comma y1 as that's the point that we know is on the line, and m is the slope. Okay, so I'll start by calculating the slope. The slope is just the derivative y prime with our known points, our known coordinates for x and y plugged in. So at the point 2 comma 3, y prime equals 2 times 2 plus 3 divided by 2 times 3 minus 2, which is 7 over 4. Okay, so there's our slope. Our slope is 7/4, and our point is 2 comma 3. And so writing the equation for the tangent line is actually pretty easy. We just need to fill in these three things that we've now solved for. So y minus our known y value, so y minus 3, equals 7/4 times x minus 2. And we're done. And again, we don't need to solve that for y. You don't need to put it in slope-intercept form. This is perfectly good equation for a line. So here's our answer for part A, and here's our answer for part B. Okay, so one more problem to look at here from the quiz, and then we can talk about some things from this week. So last problem here is a related rates problem. This is a really good transition into some of the topics that we're seeing this week. Optimization is a major topic in calculus, and that's coming into play this week. That and related rates have some very similar aspects in how the problems show up and how we approach them. In this problem, I've given you a scenario involving a rate of change. All related rates problems give you some sort of rate of change and ask you about some other rate of change. Those are the rates that are related. So in this problem, the rate of change that has been given to you. Oh, let's see. Am I still on the whiteboard, or am I on, let's see. Sorry, I'm just seeing some chat here. Travis, am I back on the whiteboard for you?
You are, thanks.
Awesome, okay. Was I by the end of the problem there?
No.
Oh no, okay. So there's gonna be a lot of talking and not much of the math for that last little part there. Sorry about that. If I get a chance, I'll go back and re-record that, but thanks for letting me know. Okay, so the last problem on the quiz is a related rates problem, and we've been given a rate of change in the volume of a spherical balloon. We've been given an equation for the volume of a spherical balloon, and then we've been asked about the rate of change in the balloon's radius. And hopefully this makes sense. If we're inflating a balloon, the radius is going to increase. So we know a few things. We know the equation for the volume of a sphere is 4/3 pi r cubed. Or I think I wrote it 4 pi over 3 times r cubed. So that's just a geometry formula. And by the way, we'll never give you a problem where you need to use any super sophisticated geometry formulas, or we'll never assume that you know those. So if we're going to do a problem involving like a tank of crude oil that's in the shape of a cylinder, we'll give you the equation for the volume of a cylinder. Same thing for almost everything else. We do assume that you know how to find the area and perimeter of a rectangle, the area and circumference of a circle, some of those basic like two-dimensional geometric figures. But the 3D stuff will give you the formulas here. So the other thing that we've been told is that the volume of air is increasing at a rate of 36 pi cubic meters per minute, maybe? Let me see, what was it? So 36 pi meters cubed per hour. Okay, it's a weather balloon, big balloon here. So the first thing that we need to do is actually interpret that given information in the context of the problem. So just by writing this equation here, I've made a couple assumptions that'll just hold for the rest of the problem. V refers to volume, the volume of the balloon, and R refers to the radius of the balloon. And since we have a rate of change that's measured in cubic meters per hour, we should probably measure all of our linear measurements in meters, and we should measure time in hours just to avoid any sort of unit problems here. Okay, so what we've been given them is that air is going into the balloon at a rate of 36 pi cubic meters. We need to interpret that as a derivative. So I could do it a couple different ways. I could write it as v prime. I'm going to write it as dv dt. Right, that's the same thing as v prime, the change in volume with respect to time. And dv dt is 36 pi meters cubed per hour. So that was the rate of change that was given to us. Even though it wasn't written this way, we had to write it ourselves. We had to interpret what we were being given and using the variables in the problem. And then we've been asked to find how the radius is changing. So we want to know dr dt. And so we need an equation that links dv dt with dr dt. Well, look what we have here. We have this geometry formula that links v and r. And so if we differentiate this equation with respect to time, that will form the connection between the quantity that we have and the one that we want. So if I differentiate with respect to time, and here I'm doing implicit differentiation. It's a lot like problem 3. I'm taking d dt, ugly t there, d dt of v on one side, and I'm taking d dt of 4/3 pi r cubed on the other side. Okay, so on the left-hand side, if I take d dt of v, it's not 1, right? Because the variable t does not match the variable I have here. So d dt of v is dv dt. And on the right-hand side, I have 4/3 pi r cubed. So again, r is related to time, right? The radius is changing as time changes. So we can think of r as being a function of time. And because of that, we'll use the chain rule on it. So our 3 will come out in front, multiply by 3, and we have a fraction dividing by 3. Those cancel, and we're left with 4 pi r squared times dr dt. And just like the last problem, right, that dr dt, that's because of the chain rule here, because r is a function of time itself. And now look at what we have here. We have dv dt, we have dr dt, related according to this equation, and all we would need to know then is the two variables, dv dt and r. Well, the last part of the problem says the radius is exactly 3 meters. So we know that dv dt is 36 pi. We know that r is 3 meters at the moment in time that we want to look at dr dt. And so then we can plug in those known quantities into our equation here and solve for dr dt. I want to know dr dt. And dv dt is 36 pi meters cubed per hour. And I'm using units throughout here. You do not need to use units throughout the entire problem, but I'm doing it to show you that it works. And the units are important in your final answer. It doesn't make sense to say the radius is growing at a rate of 1. Well, what? 1 mile per minute, 1 centimeter every millennia? You know, we do need some units in all these related rates problems if the initial problem had units associated with it. So I just plugged in dv dt is 36 pi meters cubed per hour. That equals 4 times pi. Okay, now the radius is 3 meters, so we have 3 meters being squared, and then that times dr dt. Okay, so then 36 pi meters cubed per hour. If I multiply this out, I get, well, 3 squared is 9. The meters are also squared. So I have 9 times 4 times pi. I have 36 pi meters squared times dr dt. And then to get dr dt by itself, I'm going to divide both sides by 36 pi meters squared. Right, it cancels over here. And our final answer for dr dt is, well, those cancel. That's just 1. If you look at the units here, we have meters cubed in the numerator, meters squared in the denominator, right? We have an hours in the denominator. So when we resolve those units, we will have just 1 meter per hour. And that's the instantaneous rate of change in the radius at the moment that the radius equals 3 meters. So just a couple of comments that I think are helpful for this problem, but also helpful thinking forward about the things that we've seen this week. So potential pitfalls, first of all. You'll get a whole bunch of zeros if you start plugging in numbers at the very beginning. So I started with this equation relating V and R, but I don't want to plug in like the radius of 3 meters at the beginning of the problem, because then when I take a derivative, the derivative of all those constants just goes to 0, and I end up with like 0 equals 0 as my equation, which is not very helpful. It's true, but not helpful. So I want to differentiate first, right, using implicit differentiation, and then plug in. That's a really common mistake that I see. Someone will plug in one of the known quantities a little bit too early in the problem. Let's see, what else here? I think what I'll talk about, maybe I'll hold off on this till we do an optimization problem. These problems, it's easy to just kind of wander and get lost in them. There's a strategy that I suggest that kind of holds for both of these. In this problem, first thing you need to do is just kind of wrap your head around the situation with no math in mind at all. Just like, okay, what's going on? All right, a balloon's being inflated, volume's getting bigger, and the radius is also getting bigger. Okay, so just start with generalized idea of what's going on. If the problem doesn't have variables established, you may need to create the variables. So for example, we're going to do some problems involving creating like fencing in pastures for livestock. Nowhere in the problem does it say let the width of the field be X and let the length of the field be Y. Those are choices that you can make in a math problem. You can invent whatever variables you want, invent them so that they're helpful to you in the problem, and then use them and keep track of them. So in this problem, we were sort of given the variable V and R, which was nice, but that's not always the case. Second thing I did, I said, okay, well, what do we have and what do we want to know? Well, we have dV dt, the change in the volume, and we want to know dr dt. And I kind of like wrote that as a note to self here. That sort of set up what we needed to do next. If we wanted to relate dV dt to dr dt, what we started with was the relationship between V and R. Aha, now we can sort of see where the problem's going. Use implicit differentiation, plug in the known quantities, be attentive to units, and we're done with the problem. So I think what I'm going to do, I'm going to stop the recording here just so we have one video that's just about the quiz, and then restart it with some optimization and maybe another related rates problem. So just hold on a sec while I do that.